Our goal is to review curve sketching and show an application to rational functions curve sketching. We've recently looked at basically stationary functions. Recently was covered, I should say, and basically stationary points are important because they help us sketch functions, and the goal of sketching functions is all about demonstrating your understanding of the nature of functions. So it's a way we use to demonstrate somebody's understanding of the nature and the behavior of functions of different types. So yes, sure, a graphics calculator or software will do this, but it's how do we assess that person knows more than just pressing a bunch of keys. It's by manual curve sketching. It's not just about demonstrating too. The process actually helps us learn as well as demonstrate, so you can learn a lot by doing this. Here's a suggested procedure for sketching functions, and it's 6 steps, as you can see. So first thing we want to look at is the X-Intercepts, or the zeros, if they exist. So not all functions have solutions X-intercept zeros, and as you know, set f of x equal to 0 to solve for x, or set y equal to 0 in other words. If there are any discontinuities, they're places where the actual function is not defined, and if they exist, we need to determine the points where that happens, and there may be an asymptote. Vertical asymptotes are the more common type, but horizontal asymptotes can exist, but more about that further on when we get into exponentials, because that's a classic example where we get horizontal asymptotes. So in this body of work now, we're seeing if there's any vertical asymptotes and if there's any discontinuities. The sign, whether the value of the function is positive or negative, and which intervals is it positive and is it negative, and the key points where functions switch sign, of course, are the zeros, and if there's any discontinuities, it could happen there too. So if there's a vertical asymptote, for example, it may switch its sign. It may go on from positive to a negative, or of course, as you see with polynomials, for example, as you cut through the x-axis, a function might go from negative to positive, or vice versa for f of x. The derivative is very important. It obviously, from previous work, it helps us identify the stationary points and their nature, and that links, of course, to intervals where the function is going up or going down. Okay, the gradient is positive or negative. In other words, it's increasing or decreasing. And step 5, the Y-intercept. It's a point. That's handy, gives us further information. It complements the work we do up here with the X-intercepts. So they're points. Okay, remember, intercepts are merely points, but they're key points too. They help us do a good sketch. Lastly, the behavior as x approaches positive infinity and negative infinity. So this is where we link back to prior work about the dominant term. Now, it has the biggest effect. In most functions, there is what's called the dominant term. It has, as you get big values for x, as x approaches positive infinity, and likewise with negative infinity, the dominant term has much greater effect on the function's values. So in a polynomial, it's the term with the highest power. So if it's a cubic, it's obviously the cubed term is the dominant term. So the magnitude of the dominant term becomes, much, as I said, much more influential, and it's because once you sub values in, its magnitudes are far greater. So the function does behave like the dominant term, and you may have noticed that in the past you've possibly done activities where you put in, let's say, a quartic, and you on the graphics calculator or graphing software, and you increase the domain, and if you zoom way out, the curve behaves like the dominant term. It'll behave like a pure cubic, like y equals x to the 4th, for example. The other thing that we can find too is it can help us with the asymptotes, and if there is a horizontal asymptote which won't apply in this body of work, basically as you approach positive and negative infinity, your results start to approach the value of that, the y value of that asymptote. There's also that sort of behavior too when we have the vertical asymptotes. So as we approach the value of that vertical asymptote, which will be an x equals function, you'll notice that the curve may start to approach infinity positive or infinity negative. If you're not quite sure what we mean by these things, we're going to illustrate some of these things with an example with rational functions now. We're going to sketch the rational function f of x equals 2x minus 9 over x minus 3. So we're going to find the x-intercepts. So the x-intercepts are when f of x equals 0. So let's do that first. So the zeros, or x-intercepts, okay, and that's when y equals 0, or in other words f of x equals 0. Now have a look. Use those eyes, they're not painted on. Does that have anything to do with the denominator? Have a think. No, it doesn't. It has everything to do with the numerator. So we're only concerning the numerator. It's the only thing relevant. You can't get a fraction to equal 0 unless the numerator is 0. We do not want the denominator to equal 0 because the function is undefined there. So really, therefore we're really looking at 2x minus 9 equals 0. So we have x equals 9 on 2, or 4.5 if you prefer. Alright, so we have one x-intercept. So there's the point. Okay, so discontinuities now. Alright, so we've got our zeros. Now it's time for the next phase, the discontinuities. This is when the function is undefined. So as I said a moment ago when I was talking about the denominator, the only place, if it was a regular polynomial in other words, it would be defined everywhere, but because this is a rational function, when the denominator is equal to 0, we have an undefined function. So we find out when x minus 3 equals 0, and that's when x equals 3. So it's undefined at x equals 3. So that should make us suspicious that there's probably the behavior of the curve will show us for sure that there's probably a vertical asymptote there. So we need to look at that. So behavior is what we're looking at now, and in particular as x approaches 3 from above and below. So we're going to draw a little table and show you what we mean by that analysis of the behavior. We've got a zoomed in table, and basically we've got on the top here as x approaches 3, that's, see how we've got the arrow pointing to the right, that's from below, and over here we've got as x approaches 3 from above. So we've got the arrow pointing to the left and then the arrow pointing to the right here. And we're looking at values now. There's no firm and fast rule about what's used, but see how I've chosen numbers that are getting near 3 and getting ever so near 3. So 2.9, 2.99 and 2.999. And what's the value for the function? If we sub those in, you can see it's 32, 302, 3002. That's amping up ever so quickly. So you can see the progression there. So as soon as we add just a simple another place onto the decimal, we get a drastic increase in f of x. The other end too, we see something different. 3.1, that says 3.01 and 3.001. See how that's approaching 3 from above. It's getting very close to 3 now. What happens there? We've got negative 28, negative 298, negative 2,998. So a drastic change in the values there, but they're heading to large negative values. So notice this this is heading on the right hand side from above, it's heading to a different place and it's negative, whereas these ones here are positive and they're heading to a different place. So on the last row there, from above, or sorry, from below I should say, f of x is approaching infinity, positive infinity. So as we approach x from below, the curve's going to drastically try and move up towards infinity. From above, on the other side here, we see that it's something quite different. We're heading to negative infinity. Okay, so you can see that that's the behavior summarized. So this basically means there's an asymptote, and that asymptote exists at x equals 3. So the equation of the asymptote is x equals 3, or we can say the asymptote at x equals 3. So it's a vertical line. Okay, then we've got an idea of the asymptote and of course the behavior, so the shape of the function either side of that. The other thing is that we need to know the sign of the function. So if we go back to black pen, we've got to analyse the sign of f of x. So we need another table for that one. So we've got a table started here, give it 3 rows, 6 columns. We need a row for x, a row for f of x, and a row to analyse the sign, whether it's positive or negative. So just subbing in some values for x. Now, how do we choose those values for x? Let's do a bit of reasoning. We need to look, remember, at either side of the discontinuity, which, you know, that's at x equals 3. And so we need to look at a logical step before that. The function is positive. Okay, and also remember we have a 0 back here, or an X-Intercept. Okay, so it was at 4.5, so we've got to consider that. That's not till much further along, so we're safe to use 0. Okay, it's well away from the intercept. That's down here. We'll look at that in a minute. So we can use anything before 3 that's convenient. It makes sense not to stray too far away from 3, so 0 is close-ish and it's an easy one to sub in. Okay, so the sign is positive because we get 3 for f of x, so the sign there is positive. What happens at x equals 3? It's undefined, so there's no value there. So basically the sign is therefore undefined, there's no function there. It's negative here, alright, and now the sign is neither positive or negative here, so again the sign is let's say not applicable because it's cutting through the axis there. Okay, and it's positive again here at x equals 5. So we have positive, undefined, negative, and then positive again. Okay, so the next step is to find the derivative, which gives us important information. Oh, I've spelt derivative wrong, let me fix that up. So derivative, remember we've got a quotient form, so one of the options is use the quotient rule. So that would mean that the derivative, if the top is called u and the bottom is called v, so we subbed in the relevant values there as per the quotient rule, which you've seen before. So expanding the numerator. Now be careful, as ever, students sometimes get tricked by this. Be careful, that's like -1 there. So it'll change the sign of what's inside the brackets there. Be careful always of those. So it'd be -2x plus 9. Minus negative is a plus. Okay? No point expanding the denominator. It's already factorized, and factorized tends to be the preferred way. So leave the denominator alone. You're wasting your time. Okay, 2x take 2x is 0, and -6 plus 9 is 3. So the derivative is 3 over x minus 3 all squared. Okay, so that's f dash of x, and it tells us some great things, that derivative, if I can write properly. Sorry about that. Okay, fixed. Now, one of the things that we find from the derivative is the stationary points, the nature of the stationary points as well. So stationary points happen when the derivative is equal to 0. So we've got our derivative f dash of x. So let's solve. So we're going to solve that. Rightio. So when does it equal 0? You tell me. I can't hear what you're saying. No, that's because you got no answer, have you? Because there is not a case where that function equals 0. So this thing does not have any stationary points. I told you so. You never listen. So there's no solution to that. Therefore, there are no stationary points. Okay, that's interesting, isn't it? So no maxes or mins or inflections. The plot thickens. This is getting intriguing. Don't laugh. So basically, we need to look at the basically the intervals is the next little subsection here, where the function is increasing and decreasing. So we need table number 3. No, I'm not kidding. So another table. Now, how do we set this table up? Alright, that's one of the big questions with these tasks. And they're pretty big tasks, aren't they? I mean, we're at 16 minutes into the video and we've still got more to do. And this is different to the previous table that says f dash of x. How do we set it up? We need to think and understand. So think, because you understand this, so think. Well, there are no stationary points we saw just up here. So the sign won't change from positive to negative or vice versa. So the only place where it could happen is at the part of discontinuity there, you know, the asymptote we talked about. So we have to involve 3 and a point either side of that. So 2, 3, 4, as you can see, if you can see the red I just wrote, and we think and write that. So okay, so what's the value of f dash of x when we have x equals 2, 3 and 4? Well, it's 3 for the derivative, then undefined, and 3 for the derivative. So that means the function itself, whenever the derivative is positive, the function itself is increasing here, and it's increasing here. So that's both before and after. Before and after the discontinuity. Okay, so before and after. So before and after. So before discontinuity, after rise, discontinuity, rise again. Interesting. The Y-intercept is our next major point, and when we substitute x equals 0, we get the Y-intercept, and as you can see, we've got an intercept at 0, 3. So 0, 3, it cuts through the y-axis. Behavior of x as x approaches positive and negative infinity, and I've just written the function there. So looking at the behavior of the function, just not the derivative of the function, and basically trouble is if we just subbed in, you know, big numbers or infinity over infinity, we've got some problems there. Okay, we're going to get sort of an infinity over infinity scenario, which doesn't really justify very well. So we have to do something else. Pay attention, very important. So we divide the top and bottom by x. So you can see every term and top and bottom all divided by x. Now, if you look closely, what we have to do then as x approaches infinity, this is going to result in a limit, alright, which we've looked at prior to this video, and the limit as x approaches both positive and negative infinity of this now resolved function. Now hopefully you'll see the cleverness of this approach, and you need to do this, okay, otherwise it won't justify properly. So looking at positive infinity at the top here, I've branched it off as you can see, and then we would have basically 2 minus 9 over infinity. Now 9 over infinity, that the limit of that is 0. So it's basically, it's going to be 2 minus 0 over 1 minus, that'll be 3 over infinity, which essentially is 0. So the limit of that is 2. For negative infinity, the lower branch, we have 2 minus, again that's 9 over negative infinity, so 9 over negative infinity, and let me just rub that out properly. So 9 over negative infinity, or if it helps, 9 compared to negative infinity is 0. 9 compared to negative infinity, think about that, you may even need to pause the video. 9 compared to something enormous, whether it's positive or negative, is 0. So the limit of that is 0. Don't be tricked by the negativity of it. Okay, don't be negative about being negatives. So that doesn't make sense. So bad grammar, bad syntax, never mind, we'll pursue it. And the denominator too, 3 compared to negative infinity as well, is the same comparison. 3 over negative infinity is 0, limited by 0. The upshot of that is 2. So all of that intense reasoning and just a single number pops out. 2. Okay? So f of x approaches 2. So the limit as f of x approaches positive and negative infinity equals 2. Okay, so that's the upshot of that. And if you weren't confident with that, you could check it by subbing in really big values into the function, like 1,000, then 50,000 or whatever, as long as they're big numbers, positive and negative, and you'll see that it's tending towards 2. So very important conclusion from that. That means the f of x value, or the y value, is approaching 2, so there is a horizontal asymptote. At y equals 2, okay, because it's limited there, as we've seen. Here's an example of a good quality sketch. So this is a fairly sophisticated one. What you need to do is put all of the bits together from woe to go, and the zeros, discontinuities, the behavior, consider the behavior, the vertical asymptote, the signs, and from the derivative the stationary point and the intervals where it's increasing and decreasing, the y-intercept, and that behavior which leads to a horizontal asymptote. Put all of that together and you are to by hand draw a sketch, and a good answer will have actually some of these justifications from above on it. Alright, so there's your intervals. See how it's increasing over that interval. You can see the curve. Alright, you can also see a bunch of other things. You can see the sign, whether it's positive. Okay, so yes, it's positive here, it is above the y-axis. It's negative in this interval here because it's below. Again, it's positive there, which corresponds to that positive there. You've got the the discontinuities, not the intercepts, discontinuities and asymptotes considered. We've got our X-intercept, our Y-intercept, and the behavior that you know, like as something's approaching infinity, it's going to get increasingly